Okay, so before we get started, I'll just hit on a couple of the latest news items, and then I'll poll you guys to see if you had any specific questions. Hopefully the rainstorm won't be too loud outside here. I found a couple of interesting things this week. There's apparently some activity going on with lithium-ion batteries, and they're finding that they can re-energize them, basically re-lithionize them, because I guess they lose power by losing the active ingredient within lithium. So they're talking about essentially recharging these and making them new batteries without having to recycle them. So that would be an amazing thing if they could actually create a brand new lithium ion battery. That would change electric vehicles. It would change a lot. Because of course, the big thing with electric vehicles is the lifespan of the battery. So that could be quite a dramatic thing. It's still fairly in the experimental world, but that's an interesting development.
Jay, are they adding new lithium in there, or are they somehow recovering what was soiled or damaged or whatever?
Yeah, they said it was through an electrolysis process. So I would assume it's some sort of chemical recombination of the existing element. But it wasn't that specific, you know, but it was encouraging. I mean, all of this stuff's encouraging. It may come to nothing, may be an amazing breakthrough. There was another interesting article I saw on, they were calling it agrivoltaics. They love those things like photovoltaics for solar on water, agrivoltaics. And they've been doing some experiments where they've been raising animals with photovoltaic arrays, primarily sheep, but I guess it would work with cows as well. And they found that the grazing on the lots or in the pastures has not been impacted by the solar. And what they're doing there is they're doing an east-west orientation, and they're spacing them about 20 feet apart, the rows. So clearly throughout the day, the sun hits all of the grasses essentially. So they're not creating permanently shaded spots on the pasture. And as a result, you end up with usable pasture land, but still being able to get a significant amount of solar out of it. So I found that interesting. Obviously, you'd have to raise it up high enough so the animals don't mess with it. Goats are always difficult with that. I saw an online thing of somebody who had a solar panel with goats, and these goats were just jumping up and running all over the panels and jumping off, and I thought, oh man, because they didn't raise them high enough. That's why the front of our solar array is about 5 feet off the ground or so, and so the panels haven't. The goats haven't managed to jump up there. They're lazy, so they won't. And then I saw an article about a project in the Netherlands, where in the city of Utrecht, Hyundai is putting in 500 bidirectional charging stations. So they're beginning to experiment with what we've talked about previously here, using the automobiles as a backup. You know, so they will be able to drain power as needed. And so it's a first step in that process, you know, at scale. They didn't say how deep they would discharge the cars. I looked through there to see, you know, are they going to limit it at 90% so they never drain more than 10%? They didn't get into those details, but they are starting a V2G system in that city. And you know, I think that's going to be a huge thing, where we can begin to use the storage capacity of cars as a grid storage system. So those were the three items that I saw in the news. Yeah, Ricky?
Is that for like residential or like office buildings? What was the city doing?
They just said it was 500 units in Utrecht. I mean, I've been there. My assumption is primarily downtown is pretty mixed. I mean, commercial with residential, you know, up on top of the commercial area. living above the store kind of stuff. Europe, of course, is much more densely populated. So they again didn't get into that much detail in the article, just that they were going to be doing the V2G experiments. So we'll keep an eye on that.
Jay.
Yeah.
Jay, how much would the cost be to charge up a Tesla or just regular batteries from, like, say 20% to 100%?
Well, some of that's going to depend on the size of the battery. Different vehicles have different sizes. It seems to me, I remember, well, I calculated it for my Prius plug-in that I have, but that only has about a 35-mile range for the battery. And it cost, it takes 7 kilowatt hours of power to charge it from 0 to full. So that's 7 kW. If you're assuming, let's say 18 cents a kilowatt hour, it would be, what's that end up being? Yeah, what, $1.50, let's say,
yeah.
$1.50, and you get 35 miles out of it. So, that would be comparable to a gallon of gasoline for a typical car. So that I think is a pretty safe average. You're going to pay about a, comparable to about $1.50 a gallon for that kind of thing, more or less. Now, if you have solar, that can come way down because then you're using it as a storage of power that would have otherwise not have been harvested. So, yeah, Bill, you had a question?
Yeah, I'd just like to add to that. We have, as the EV batteries get larger, there becomes a point in time when you literally can't charge the vehicle overnight, assuming you just have 240 volt power. And, it's a time thing, right? And they're talking about 500-mile range vehicles, and I don't know whether that's a combination of I can't imagine it's a combination of improved aerodynamics and rolling resistance to the extent that the battery isn't huge, right? So and maybe that's a reason for public charge stations, fast charge stations, level 3, charging at 480 volts. Anyway.
Yeah, well, and of course, the process of a lithium-ion battery charging is when you talk about the amount of time that's involved in charging it, you can charge 90% of the battery very quickly. It's the last 10% that takes the vast majority of the time. And from what the manufacturers say, there's no impact on the life of the battery if you don't charge it to full. So most of these charging systems are really going to be based on, quickly charging the first 90% until you get home, then you top it off. So there's a lot of advantages there. I think a lot of companies are going to install charging stations to keep you in their business, buying crap, while you're charging your car. And then, of course, you're going to find campuses, universities, communities who begin to use it as a UPS for their school or their environment. I could see a school having a lot of charging stations, and then basically they have a UPS device for their entire campus if all the students are plugged in, or office parks or things like that. The big thing there is just the bidirectional nature of the batteries of that charging impacts the warranty aspect of the vehicle. So they have to work through all of that because, when Tesla makes a car and they guarantee it for a certain number of miles, that's assuming you're not, leaving it in your garage and charging and discharging and charging and discharging every single day. So that's something that we got to work through. But, when money's involved, people figure out stuff. So I suspect they'll figure it out. Okay, yeah, Bob?
Yeah, it's very conceivable that because there's a computer on board, your car's that they're keeping track of the charging cycles that are being subject to the car over the life of the car, and can have an algorithm in there that can figure out what the life of that battery still is based on the actual usage.
Yeah, that rather than basing their warranty on a per mile thing, they could base it on a, you know, amp hour charge discharge or kilowatt hour charge discharge rate, whatever. It's already a little confusing because, like, for instance, with my vehicle that's a hybrid, but a plug-in hybrid, the vast majority of the miles are electric if you're going short distance, but the other miles, you know, you use the engine. So what is the life expectancy of that engine? Normally you would say, you know, 100,000 miles or whatever, but over the course of 100,000 miles, you may find you're only using the engine for 50,000 miles. The rest is the motors. But then the drivetrain gets used for the full 100,000 miles. So it's already getting to where it's a disrupted technology. They'll just have to sort it out, figure out how that stuff works. But of course, the biggest issue has always been the batteries. People shy away because they say, all right, if I buy a, you know, a car with a lithium ion battery, then what happens in 7 years if I have to replace the battery? Well, that's half the cost of the car. So do I want to invest in that? Usually they're just simply warranting them. Like Toyota, to overcome that, just said, hey, we'll guarantee the batteries for 100,000 miles or 10 years or whatever it is. If it fails before that, we'll replace it at no cost. So they'll come back with something. And of course, as this lithium ion thing comes to be, then you don't even have to worry about it. You just have your batteries recharged and away you go. So, all right, any solar questions here before I jump in? Yeah, Bill?
Do you get the sense, in reading that article regarding bringing lithium-ion batteries back, that it is a new chemistry altogether, or an external process that can work on existing batteries?
Yeah, well, that's what it's designed for, is for existing batteries. And basically, you know, it was basically taking old batteries and making them new again. Now, how they do that, like I said, they said it was an electrolysis process. I don't know, but it really, that was the whole point of it. You've got an existing battery, it's existing technology. Rather than having to recycle it down to its components and then rebuild a new unit, you can take the old unit and revitalize it and use it. So that would be a game changer. And I know I mentioned last time, I believe, you know, they are actually now working with the nighttime solar panels as well. That also is a new technology that's in the experimental age. And I think when you get these new technologies in the experimental, I wouldn't look for them commercially for another 10 years or so, I would imagine. Yeah. Sometimes things happen faster, but, you know, I think we're getting the first peek at it, you know, so don't hold your breath. We'll find out. Okay, any questions? On,
on testing a used panel, I understand you can measure the open circuit voltage in presumably good sunlight, but you have no, you know, the input power is, I guess you just assume it is 1,000 watts per square meter. I know it's very scientific. The panel manufacturers flash the panel somehow with a known amount of radiation and determine the wattage based on that. Are you aware of any test equipment that can be used or test setup that can be used for testing used panels?
Yeah, typically what you would do is you would get an irradiance meter, you know, put it at the angle of the panel. They have some that clip on the side of it so that it's directly at the angle. And there is another unit, well, you would clip the irradiance meter onto it and then attach a thermometer to the back of the panel. And that unit itself will then make the adjusted calculations based on irradiance and temperature against standard test conditions and give you a reading, because you typically would adjust irradiance for amperage and you would adjust temperature for voltage. And then you would end up with something that's approximate to tell you if it is operating close to what its STC rating was.
And is it close enough, safe enough to just measure VOC and I short circuit, or do you actually need to sweep the curve and calculate the best operating point?
Yeah.
In order to rate the panel as to what the wattage is compared to the nameplate value.
Yeah, I think you really do have to have a measurement of amps as well, somehow. You know, and because you are adjusting irradiance for amps. And I mean, I would probably be satisfied to just test the VOC unless it was an expensive investment. You know, if I'm only buying a couple of panels and I just want to check it without going crazy on it, I'd probably feel comfortable enough adjusting the VOC for temperature and getting something that's pretty close. You know, because you have the temperature coefficient as well. So for every degree variation from 25 degrees Celsius, you would just make that adjustment. So that would work fine, you know, enough. But if you're doing this commercially, or if you're doing it for a whole bunch of stuff, I would get or rent or get that unit that'll let you test it. Not quite sure how you would test for amps unless you're shorting it out some way or it is hooked to a load, because you know, that's the only way you're going to get amps, is if there's a load serviced. Okay, any other question before I jump into what I thought I would do is maybe walk through some design of a small microinverter system. I know some of you guys who have been through the class, we've done this, but I just wanted to kind of document it, bring up some of these issues, partly because I'm going to have to do this in a class in about an hour anyway. So I thought, okay, I'll do a twofer here. So let me jump into the screen share. If anybody has any questions, be sure to ask. Well, this is the project that we're going to be building the solar array on top of. Here, we're going to do this at the end of May. And it's a small little pavilion. And so what I'm showing you here is that the support rafters are on 16-inch centers set across there. And if I look at the top here, this gives me the dimensions of the roof surface itself. I can get the angle. It is oriented to south, so it's going to be 180 degrees azimuth. So this gave us the working area. And then we also know that the supports have to be mounted in to the rafters. So what this is telling me is that this is going to be a portrait orientation, because the rails are going to go across the supports so that they're being supported at multiple locations on multiple rafters. Well, since the rails are going horizontally across here, then the panels will go vertically on top of those rails. So this will be a portrait orientation. And as it turns out, the space that we have will allow us to do 2 rows of 5 panels in each row. So that's kind of how we came up with the maximum amount of space there. Now the issue was, in this case, that the let me find the, oh each time. Yeah. So here, what we couldn't do is say, okay, what's our load demand? And then size our array based on load demand, because the restrictive nature of this site was the size of the roof. So what Tim wanted, where we're going to be installing this, is he said, just put as many as will fit on this thing. It's not going to service its whole load, but it's going to provide some power. So we already know we've got 10 panels. So then, of course, the next step you would do is go into PV watts. I plugged in his address here in Columbus, Ohio. So this is going to give us PV watts. Okay, what's the deal? Did I lose something? All right. Copy that. So it must have died on me. Okay. All right. So now we also know these happen to be 400-watt panels, and there are going to be 10 of them. So this is going to be a 4 kW system. The array, it's going to be fixed. PV Watts wants you to put in system losses. So in this case, it's going to be an N-phase system. And we know that the N-phase inverters only have about a 3% loss on the inverters. So let's calculate maybe 2% for voltage drop, and maybe another 1% for connections, things like that. So I'm going to say a 6% loss. And we'll leave it at a 20-degree tilt. I'm not quite sure what the tilt is. You can put in your rate. You know, we'll just leave that at its default because I don't know what his rate is. That's just used when you're wanting to calculate savings on this stuff. And what this is going to tell me is this system now is going to have about a 4.62 average daily insolation, or 4.62 hours of 100 watt per square meter sunlight. And over the course of the year, it's going to generate 5,729 kilowatt hours. So assuming it's a normal home, you know, we learned before, if we look at national averages, I think Tim's is a little less, but let's say 900 kilowatt hours per month times 12. So the average home is going to use about 10,800 kilowatt hours over the course of a year. So this array is going to generate somewhere around 60%, 55, 60% of their needs. So if we're wanting to figure out, you know, exactly what size array we would need based on the needs, you know, we could use that 4.62. We would find the daily load. We divide that by that, and then we derate it based on your derate, you know, of 0.94 in this case. And we would end up with our size. But the size would be somewhere around, my guess, on this, it's a 4 kW. So somewhere around a 7 kW would be enough in this location at that orientation to service their whole house, assuming it's basically average. So hopefully y'all remember how to do that with the PV watts. Then the next step is to start selecting some material. And I'm going to use an Iron Ridge mounting system. So in the Iron Ridge, they have this design tool. I plugged in the number here. Can you guys see this? I just switched from one screen to the other. This should be, okay, good. This is the house here. And what he did is he built this array. I think if you can see the hand moving around. I'm looking at you, Bill. Can you see the hand move around? Okay, good. Yeah, so the array is going to be right over in here. Okay, so so that's where that pavilion is being built. That's going to be the location. So then with Iron Ridge, we can start to plug in some stuff. One of the things they ask is, well, it automatically, because based on the address, puts in what the wind loading, the snow loading, things of that nature are going to be the risk categories. So you don't have to calculate that. That goes into the calculation. I picked the panel. The panels we've selected for this are going to be 400 watt Jinkos. That just turned out to be what the distributor had at a good, reasonable price. So we plugged that in. Then it's a metal roof. We're going to use L-foot. You can see that there are different options. You can have shingle, slate, whatever, but this is going to be metal. We can put in this case, with metal, there's only the L-foots, the bolt attachments. It'll ask you how high this thing is. This one's just, pretty short. What's the roof slope? I just put in 18 degrees. And the rafter default is going to be 16-inch on center. I looked at this number here, the Spectral Acceleration. I'd never seen that number before, but when I clicked on it and looked to verify it, it was talking about seismic activity and stuff like that. So I'm assuming that's its primary issue, is how much stress is going to be on it based on your seismic activity in the area. And then it asks you to design. You can design your roof sections. I did that with, in this case, it's going to be portrait, rafter spacing 16-inch on center, and we're going to have 2 rows, 5 panels in each row. You can set it up here and it'll do it that way. So it's giving you a little graphic representation. It's asking me, what is the rail system? We're going to use the XR1000. That's the cheaper of it. In this case, we're going to use 14-foot, cut them on site. And then it begins to populate the material that you're going to need. It's going to tell you the weight on that. The distributed weight of our system is going to be 2.6 pounds per square foot. That's the dead load. Remember, the live load could be much, much higher, as much as 50 pounds per square foot because of the wind pressing down. We've got 10 modules, 580 pounds for the total system. And then if I want to see my bill of materials, I can go in and let's see, do I have to, oh, here, yeah. It's going to give me a retail price. And now it's telling me 17-foot. It turns out I'm going to need 6 of these 14-foot or 11-foot, I think is what we're getting. But it's telling me how many of the clamps I need, how many of the stopper sleeves, how many grounding lugs, the foot attachments, what they're going to be. So it's telling me my rail system is going to cost me about $689, $690 there. Yeah, John? You'll need to unmute.
Are the rail systems and panels pretty universal, that they all kind of mount to each other?
Yeah, not 100%. Some railing systems require specific panels. I'm thinking about some of them that clamp on the sides. There are panels that have channels that you'll clamp in, but 95% or better of the time, these panels are all, the railing systems are designed universally to meet the need. And you will notice in here, when I selected the panel, it is going to tell the height that the clamps need to be. These panels happen to be 40 millimeters thick. So the clamps and the stoppers are all adjusted to meet that. There are a couple of universal sizes, thicknesses of panels. That's usually the biggest issue. So all of those are coming in and it automatically populates that. Yeah.
So then on a metal roof, you have the ridges, right? So then these brackets are designed to compensate to get it above the ridge, or how does it know how big that ridge is?
Yeah, some of the metal roofs have those ridges. Some of them don't. Some of them are raised seam, and they do have clamps that you can just clamp on the raised seam. But in this case, what we're going to do is these things are L brackets that have a layer of bitumen on the bottom. So we're going to fit them in the flat part of the metal. So we'll set it up so it fits there. We have enough flexibility to do that. But I have seen some mounts that are designed to go over like those 5V units. So you can get bits that work with almost anything. Okay, any other questions on this stage of it? So then
One
yeah,
question.
yeah.
How long generally do you order these materials out from when you start your project?
Yeah, that can be dependent upon your distributor. What we found with this particular one is the materials we're going to get is from a Columbus-based distributor. So I think for the most part, he can just go down and pick them up. But we have tried to give at least 3 weeks lead time on this. And of course, if you're having them shipped, that can be all over the place. You can expedite it by paying extra shipping. But yeah, hopefully you'll give yourself at least, say, a month lead time to get everything ordered, because things happen, especially what I'm telling Tim is let's make sure we have all the materials there at least 10 days ahead so we can look them all over, because if there's a problem, we don't want that problem to be on the installation day. We want to be able to resolve the problem. Let's say a couple of the panels come in damaged, or they sent the wrong rail, or they didn't send enough of something. We want to be able to address that before the install date. So, as much lead time as you got, it's like any other project. The more you plan ahead, the better it's going to be, the smoother it's going to be. And I see Tim, we're talking about your project. So Tim Chavez just joined us up, so he can look at these things as well. So this is a really handy tool for designing your system. You can pay them to put together a permit pack. Seems to me, let's see. Oh yeah, I got to sign up. I don't really want to pay for that. What I did, let me stop share that. I'll bring up what we created here. Let's see, I guess I gotta hit share. Yeah, the materials list here. So what we started creating here is I took some of that information, took other things. This was the original materials list for the project. Got the solar panels here, 10 of them. The N-phase IQ7s, which are the microinverters. And those are good for 60 and 72 cell panels. So be sure that your microinverter works with your panels, because notice these are 72 cell panels. So we got to have a microinverter that'll work with 72 cell panels. This particular model will work with either one. Those run about $149 a piece. Then we've got the bonding hardware, the T-bolts that attach them. So we got to make sure we have those. We're going to have the cables, the proprietary cable that goes with it. Notice we've got 10 panels here, but I've got 11 of the cable ports. And that's because, as the wires go, they're going to be going 5 across, and then they've got to make a loop and go down 5 on the bottom. And that distance between the ports, I need to leave one unused. Otherwise, the wire won't reach. So you end up getting 11 of these instead of 10, but we're only going to use 10. And then you've got to have a little sealing cap for the unused one. And then the big thing here is the combiner. I'll show you some information about that. The end terminator. So we terminate one set of the wires at the where we're going to run to the home. The other end is just bare wires. So there's a little termination kit that you get for that. We're going to put a surge protector on the unit. We've got some breakers and plugs, and then down in here we've got the Iron Ridge stuff, and I got that simply from that Iron Ridge supply thing, or that design.
The Envoy at?
Pardon?
Where's the Envoy unit at?
It's built in. It's built into this combiner box. This $675 combiner. The
Okay.
Envoy is now built into that unit, and it's a pretty slick system. You don't have to then worry about wiring it up. It's already there.
Right.
You just connect this thing to your service panel. So and it actually gives you 4 240 volt ports, or double pole breaker units in this combiner. So we could run up to 4 strings, or we could run 3 strings and a battery if we wanted to hook in there. Or one of the things we're going to do with this unit is run 1 string in, not technically a string, a branch circuit. And then we're also going to run power from that back to the pavilion. So we're going to use a 120 circuit that goes back out to the pavilion from that Envoy combiner box. So we don't have to go inside for that. Yeah, Bill.
So you're saying there's a combiner within that box, and you can combine 4 strings of 240 volt AC, or 3 and a battery. That implies that the battery is got an inverter on it. Is that correct?
Yes.
Okay, I'm with you.
And all of those systems will have a battery on it, because it has to or an inverter on it, because it has to convert from the DC to the AC to service the house. So yeah, most of these units, like a Tesla Powerwall or a the Enphase has their own system. It has a second inverter. Actually, it's kind of interesting, the Enphase system. If you open up the box, what they've done is put a whole series of microinverters in there. So instead of having a single inverter, theirs has a little bank of however many of the microinverters you need for the amperage.
Oh, wow.
So that's kind of interesting. Yeah, John?
Yeah.
So the microinverters are taking the panel DC voltage and transferring it to 240 volt pure sine wave AC.
Correct.
Correct?
Yeah.
Okay, but it's not 240 120 volt, it's strict 240 volt.
Yeah, it's 240. So it's got to come in and connect to a double pole breaker.
Okay.
Or it could be 208 3-phase. These systems will
Well,
do either,
Okay. But there's no app in there to give it 240 120.
Well, from the output of that combiner, you could connect out just one single pole. But that wouldn't, like you're going in, like you get 240 from the utility, but you can service a 120 load just by going from a single part of the bus bar.
Well, that's what I'm asking, but you have to have a neutral reference point. And if these inverters are only putting out 240 volt, where's the midpoint reference point in any of that? Is it coming back from the panel?
Yeah, their output is their output's going to connect into your service panel.
Okay. But if you wanted 120 volts at the pavilion, you have to bring that back out from the internal service.
I think you're probably right, although I'm not sure if there's a neutral and a ground bus bar in this unit. I'd have to look at it. Why don't we pull that up and take a look and see? Maybe
these are the questions that I gotta know.
Yeah,
I gotta know this.
We'll know it. Yeah, because John's going to be doing the. Let's see. Here we go. Yeah, you're going to be doing the electric. So here's the That's the IQ. This is the combiner box here. Okay, so what I wanted to show you here, this is what the unit looks like on the outside. And basically it looks like a sub panel. Now we don't have enough detail there to see if you can, oh, I know one thing that yeah, now it
I
has
saw
a,
the specs. The specs did say 240, 120 on it.
okay, yeah, because I think it does have a separate 120 outlet in it. So we could connect to that. Okay, it has up to 4 2-pole branch circuits, breakers, which we have to provide. It is rated for up to 80 amps from all the branch circuits. And let's see if there's anything else there. 5-year warranty. The circuit breakers. Yeah, right here is an accessory receptacle that carries 120. So that's built in. So I'm assuming that's pulling it somehow from your connection. We'll just have to look at that when the unit comes in. But that's what it's designed for, is for you to plug stuff in at 120 directly there. So
But if you look down under electrical specifications, second line system voltage, it says 120, 240 AC. So there must
Okay.
be some kind of tapping.
Yep.
All right.
All right. So, and I think the output one might only be 10 amps. Let me see. It seems to me I have that in my mind somewhere. So the power going back out there to the pavilion may be limited to 10 amps. Shouldn't be a problem. Okay, so this tells you what this particular unit is for. I wanted to show you also the IQ7s, which is what we're going to be using. Just to let you see, the output here is for this IQ7 Plus, which is 295 volts output. So bear in mind, this panel is 400 volts DC, but the AC output is going to be limited or clipped at 295. And I don't want to go into clipping here just now, but that's fairly common. Very few days of pure standard test condition sunlight. So that's usually a more effective way of designing your systems. But at that output, it's going to generate 1.21 amps. So if we calculate this for wire sizing, the proprietary cable is 12 gauge. So what you'll find, they'll give you this specs in the installation. They'll say, if you're doing a IQ7 Plus, limit the number of inverters to 13 maximum. And if you do the math here, you'll find 1.21 times 13 gives us 15.73 amps. And then if we multiply that times 1.25, which is the NEC safety margin, we're at 19.66 amps, which is under the 20 amp threshold rating for 12 gauge cable, copper cable, at its lowest temperature rating. Okay, now, so that's why they tell you to limit it to 13. If you're doing it at 208 or 3-phase, you got to limit it at 11. But our branch circuit is going to be 10, so we're going to be fine. We couldn't do more than 13. If we were doing, say, 15, we'd have to break them into 2 branch circuits and then combine them in that combiner box. We could balance them or we could leave them unbalanced. That doesn't matter for this particular application. Okay.
Jay,
Yeah.
just a 10-second comment. What do you think about IQ8s? And do you know the price of them?
No, I've never actually used those. I think they're primarily designed for bigger panels, aren't they? They're a higher. Dual port.
Yeah.
Yeah. So that's a good thing if you're trying to save some money and you're not dealing with any shading issues. because obviously 2 panels are then going to be on 1 inverter. So if one of them shaded, it impacts the other one. So that's the downside. But if you're doing a large array and you've got, say, 40 panels, now you're talking about 20 inverters versus 40. So
Right.
that would be a good deal.
Okay.
Fairly common. All right. Yeah, John, I had muted you there. So John, you'll have to unmute.
Okay, so if we are, the microinverters are physically at each panel.
Correct.
Is that correct?
Yes.
So then they are putting out a 2-wire AC voltage of 240 volt.
Correct.
So the physical connections are going to be a 2-wire cable. Whereas if this was a DC string inverter, they'd be in series. It would just be a single conductor going through a series string.
A single hot. There'd be well, no, if it was a string, it would have a positive and a negative because it would be a DC circuit. So
Yeah,
it would
but
be
if they're in
different.
series, if they're in series, it would just be one to the next, and it would have to have a return at some point.
Yeah, which is the negative.
Okay.
Yeah, it's different nomenclature with DC versus AC. You're used to having a hot wire and a common or a neutral, but in DC it's going to be a positive and a negative. So there. Now with the new wiring system, with the old N-phase wiring system, it used to be that there were actually 4 wires that were part of that proprietary cable. There was a neutral, a ground, an equipment ground, and 2 hots. And they all hooked together and you just ran it like a regular 240 circuit. But the new proprietary cable only has the 2 hots. There is no neutral and there is no equipment ground with that cable. So that confused me at first. It may not confuse you, John, but it confused the heck out of me not seeing all 4 of those wires. But their argument, I guess, is there needs not be any common on these, and that the equipment grounding is taking place through the frame of the microinverter. So,
It's just got to work, and there's a million ways to make it work, but I can grasp that. Yes.
okay.
Okay.
All right. Any other questions on that, on the inverters there? Or I move on? Show you the 1-line drawing here. This is what we put together for Tim here. And it has, site information, size of the system. This is one we did when we thought there were going to be 12 panels. So we might have to, for your permitting there, Tim, we might have to do this again. And it just gives the module information, the equipment information, the array information, and then it gives a schematic, just a 1-line drawing of the array, hook it into a combiner box. In this case, it's not really a combiner, it's a junction box. Then we're going to the combiner box for the branch circuits. Then there's an AC disconnect out here. Then we go to the service panel, and of course the service panel is already hooked up to the existing meter. So it's pretty simple, pretty straightforward. So I think that's fairly straightforward there. Let's see, what else did I want to show you? I showed you the canopy, the wire design. Yeah. Okay, so that's going to be basically, yeah, John?
Sorry, but so does Tim need to have some kind of agreement with the utility AEP before he does this, or are they just obligated to take it?
Yeah, there's typically there's a net metering agreement and an interconnection agreement. Those are fairly standard forms. So yeah, Tim, if you haven't contacted AEP to tell them that you're going to be hooking up, you're going to need to sign that agreement. Not like you have a lot of choice. They're going to give it to you and you're going to sign it. But they're also obligated to accept it because by state legislature. They have to let you hook up as long as you meet their issues. And some of the things that are in that agreement there are two agreements, but it's one document. The net metering talks about money. So it says, okay, we're going to pay you this much for your power. You're going to pay us this much for your power. How much is the connection fees that we charge, that kind of stuff. The interconnection talks about you may have to have insurance on your homeowner's policy that covers for liability issues. That's another thing to double check. You have to use a UL 1741 rated inverter so that you don't have anti-islanding issues. Well, Enphase meets all that. You know, they also are going to be requiring the disconnect switch. So those are the things they're mostly worried about. Is the inverter has to be rated so it shuts off if the grid goes down. There has to be an externally operated disconnect, and they need to be labeled. Those are usually the big items for the utility. But just got to get that thing signed. It's usually fairly straightforward. They have a standard form. You fill it out, you sign it, you're done. If you have to have insurance, the insurance for me, for my array, I needed to have like $500,000, I think, liability. When I contacted my homeowner's insurance, they said, well, you already have like 300,000, you know, and that's the same liability if somebody slipped on your sidewalk or whatever. And they just increased it to $500,000. And it added like $8 a year to my homeowner's policy, something like that. So that wasn't a big deal either. Okay, so that's a pretty straightforward, yeah. Bill? You're muted, Bill. Bill, you're muted.
Back to the combiner box. When you have a battery on there, is that called an AC coupled system?
Yes. Yes,
Okay.
for that particular one. And Enphase has a nice system specifically designed to interact with this particular combiner box. So what they have is you would end up buying two more units. There would be the battery that's coupled with an inverter, you know, with a bimodal inverter. And then there's a transfer switch or you know, something that will disconnect you from the grid. So those two units hook into this same system, and we'll see there are plug locations in that unit for those. So that's one of the reasons we decided that even though we're going with just one string on this or one branch circuit, this will now allow us in the future to add, you know, at least, you know, to really triple the size of our system if we needed to, although I don't think there's room on the site. And but we could put them on the house, on the roof, and also to incorporate batteries at some future date as well, without having to get John to come in and redo all the wiring. So that was part of the goal, to future-proof, get everything future-proof. Okay, anybody else? We got less than 5 minutes here, so I'm assuming, all right, great. Well, then we'll get together next Tuesday at noon. Thanks for your attention. I'll see you guys then.
All right.
Bye-bye.